Hello. So in a previous video we discussed the laws of indices. What we're going to do now is consider how some of those laws of indices can be applied in manipulation of equations. Particularly we should use some astrophysics examples, which is quite helpful. So we're going to start off with something known as the Tully-Fisher relation, which is something that's related to galaxies in astrophysics, and it says that the luminosity scales in proportion to the fourth power of the rotational velocity, which is quite useful to know. And so we're going to start off by saying that a galaxy has a total mass of m, and it can be expressed in terms of a luminosity, and we're going to say it's given by some term upsilon, it's a Greek letter, times luminosity, and where upsilon is proportional to velocity to half, and this is something known as the mass to light ratio. And we want to express m in terms of the luminosity, and so we've got this term here, mass is equal to upsilon times luminosity, and we simply substitute for the velocity to the power of half into this equation, and this becomes velocity to the half times by the luminosity. And since we know that the luminosity is proportional to the velocity to the fourth, as given by the Tully-Fisher relation, we can substitute that luminosity into here. So now we have mass is equal to the velocity to the half times by the luminosity, which is given by velocity to the fourth. And we're going to combine these two indices, so it becomes velocity to a half plus 4, which is velocity of 9 over 2, or 4.5. And one of the ways we can check this, there's a little trick we can do, is we can look at these powers in isolation. So we start off with a half, and then we had plus 4, which is really 4 over 1. We've added its two fractions like this. And what we can do to check this is we can multiply both the numerator and denominator on this side by the denominator on this side, and multiply the numerator and denominator on this side by the denominator on that side. So this becomes 1 times 1, which is 1, divided by 2 times 1, which is 2, plus 4 times 2, which is 8, divided by 1 times 2, which is 2. So now what we've done is on both sides we have 2, which means we can rewrite this as 1 plus 8 over 2, which is simply 9 over 2. You see, which is what this relationship is here. And so our final relationship is that the mass is proportional to the velocity power of 9 over 2. Therefore, if the luminosity scales as velocity to the power of fourth, and the mass to light ratio scales as the velocity to a half, then we've shown that the total galaxy mass scales as the velocity to the 9 over 2, or 4.5. And so it has a strong dependence on rotational speed. So that's the end of that example. Let's do a different example for the gravitational potential per unit mass. And we're going to be dealing with stars. So gravitational potential is given by this term phi equals minus g, which is the gravitational constant, times m over r, which is the radius from the centre. Now suppose that the mass inside of the radius is given by a power law that looks something like this. Mass is equal to a r to 3 over 2, where a is some constant of the star density, for example. And then we can substitute that into our equation for the gravitational potential, which is equal to minus g over r, and then instead of m we've got a r to 3 over 2. Okay. Now we notice here we've got r to the 3 over 2 and we've got r to the power 1 on the denominator. So let's look at those and treat those in isolation. So we've got r to the 3 over 2 and r. That's the same as saying r to the 3 over 2 times by r to the minus 1, which is equal to r to the 3 over 2 minus 1, which is equal to r to the power of a half. And so just to check this, again we're going to use our little trick of writing out the indices. So 3 over 2 minus 1 over 1, multiply the top and bottom again by the bottom of the other side, and this gives us 3 divided by 2 minus 2 divided by 2, which is equal to 3 minus 2 over 2, which is simply 1/2, which is what the power is we've ended up with here. And so writing out our final term for the gravitational potential, minus g a r to the power of a half. And this tells you that the gravitational potential per unit mass increases, becomes less negative with distance, as r to the half in this model. And this is different from a usual minus 1 over r gravitational potential model. And situations like this might occur, for example, in a star which has regions of different density. Let's now consider a more complicated example, and we're going to look at something called the radiative transfer equation. Radiative, of course, refers to heat, energy exchange, and it says that the energy flux in a star under what's known as the diffusion approximation is given by F is equal to minus 4 AC over 3 kappa rho, temperature to the power of 3 times by a derivative of temperature over R, which is really referring to a gradient in temperature over distance. We'll call this equation 1. A here is a radiative constant, c is the speed of light, kappa is a term which we refer to as opacity, and T is the temperature. Now in stellar interiors for stars, the density can be modelled with something known as a polytropic equation of state, or an ideal gas equation, and it's given by something like the density is related to rho naught T over T naught some power n. Rho naught and T naught are reference values, and n is some fractional power index. So for example, if n is equal to 3 over 2, this is something you might experience in a fully convective star, in which case rho is equal to rho naught T over T naught to the power of 3 over 2. So that's our equation 2. And what we would do now is substitute equation 2 into equation 1, because we've got density on the bottom here. And what we end up with when we substitute this is that the flux is given by minus 4 AC divided by 3 kappa. I'm going to put rho naught here, T naught over T, 1 to the power of 3 over 2, times by T cubed, and then dt by dr. And this is known as a generalized energy flux equation, where temperature and density are related through this fractional power. And we can check, we now have a T here to the power of 3 over 2 and a T to the power of 3. And so let's just treat these terms in isolation to see what this looks like. So we've got T cubed divided by a T to the 3 over 2, because T naught is a reference temperature. And we want to combine these, so this is simply T to the cubed times by T to minus 3 over 2, which is the same as T to cubed minus 3 over 2. And we can use our little trick just to check what that would be. So it's 3 divided by 1 minus 3 over 2. And we multiply top and bottom of both by the denominator of the other side, and this gives us 6 over 2 minus 3 over 2, which is equal to 3 over 2. And so we end up with a temperature of 3 over 2. And so now if we write out again our radiative transfer equation with this substituted term, we end up with F is equal to minus 4 AC over 3 kappa rho naught T naught to 3 over 2 T to the 3 over 2 dt by dr. And if we create a new term called K, and we wrap a lot of our constants and so forth into that, just to make it simple, so all inside of there, and then we can rewrite the flux as this K term, temperature to 3 over 2 times by the gradient dt by dr. And this is our new radiative flux term. An equation like this is often used in stellar envelope models, such as white dwarf cooling, for example. And so we've seen here how we've combined the terms, the indices for the temperature, to end up with a new equation. That's it.